Consider the reaction between solid zinc and a solution of copper sulfate to form zinc sulfate and copper metal. So zinc is a silvery metal and copper sulfate is a bluish solution. Zinc sulfate is a colorless solution. Copper metal is an orange solid. So when this reaction occurs, silvery solid metal is mixed with a blue solution. The zinc metal dissolves and the blue color of the copper sulfate solution fades as the copper is converted into copper metal, and the copper metal falls to the bottom of the beaker. So here's a simple animation that I put together showing this reaction. If you have a solution of copper sulfate and a bunch of small pieces of zinc, you can imagine adding a piece of zinc to the copper sulfate. The zinc will dissolve and cause some of the copper to convert into copper metal, and as a result, the blue color of the solution will fade somewhat, and you'll get some orange solid copper metal in the bottom of the beaker. If you were to add a second piece of zinc, the reaction will continue. That zinc will dissolve, causing more copper metal to come out of solution, and the blue color will fade further because there's less copper sulfate dissolved in the water. Add another chunk, reaction continues. More copper metal is being formed, and the blue color is getting fainter and fainter as more and more of the copper sulfate is converted into the copper metal. Eventually, if you keep doing this, you get to the point where all of the blue color is gone and the copper sulfate has been used up. It's been converted into zinc sulfate and copper metal. And so if you were to continue adding pieces of zinc, the reaction wouldn't go any further. Once all the copper sulfate is used up, any additional zinc is just going to sit there. So the point of the reaction where all of one of the reactants has been used up is called the end point of the reaction. Prior to that point, we have unreacted copper sulfate. The copper sulfate is present in excess, and you can literally see that in the beaker. That's the blue color of the solution is coming from excess copper sulfate that has not reacted with zinc. But then beyond the endpoint, if we continue adding zinc, then that zinc just sits there and we've got excess zinc beyond the endpoint. And so at the endpoint is where you have a precise stoichiometric ratio of the copper sulfate and zinc. Each of them fully reacts with the other. So if you imagine that we didn't know the concentration of the copper sulfate in this reaction, but if we knew that we had, say, 250 milliliters of the solution, and if we knew that we had to add 3.5 grams of zinc to reach the end point of this reaction, we can take advantage of the fact that at the reaction endpoint, the added zinc has fully reacted with the copper sulfate solution, and so knowing how much zinc we needed to add to get to the endpoint, we can figure out how much copper sulfate there was to begin with in the solution. And the idea is you would take the 3.5 grams of zinc, convert that into moles by dividing by the atomic mass of zinc, and then the reaction stoichiometry tells us that 1 mole of zinc reacts with 1 mole of copper sulfate, and so there was 0.05353 moles of copper sulfate in the original solution, and then we can turn that into a concentration by dividing by the volume. 250 milliliters is equivalent to 0.25 liters, and so we find that the concentration of copper sulfate was 0.21 molar. So this technique of determining the concentration or the amount of a substance by reacting it with a second substance is called titration. Titration is the process of determining the quantity of a substance A by adding measured increments of substance B. This is the official definition according to the International Union of Pure and Applied Chemistry. Now, in the example that I just showed you, we started with a solution and then we added small amounts of solid to it. And when we do titrations, we are normally measuring the amount of substance in a solution, but it's more common that rather than adding a solid, that we'd be adding a substance that's also a solution. There are a variety of reasons for this. One reason is simply that it's easier to precisely measure the added amount of a liquid than it is to slowly add solid and precisely keep track of how much you've got. And so you're very often adding one solution to another, and very often the end point of the reaction is not obvious by itself, as it was in the case of the reaction between the zinc and the copper sulfate. And so often when we're doing titrations, we need to use something called an indicator to help us spot the reaction endpoint. And the indicator is just some sort of substance that changes appearance at the endpoint of the reaction. And so one very common example is in titrations of acids and bases. One will often use an indicator called phenolphthalein, and before you get to the reaction endpoint, the indicator is colorless. When you reach the endpoint of the reaction, the indicator takes on a very pale pink color, and so that's what you're looking for when you do the titration. And if you were to go past the endpoint, then the indicator takes on a deep pink color. And so indicators give us a way to spot that endpoint of a reaction. So I want to talk about a typical problem that you might encounter in a textbook that is talking about titrations. So here we've got a problem. What is the concentration of sodium chloride in a solution if titration of 15.00 milliliters of the solution with 0.2503 molar AgNO3 requires 20.22 milliliters of the AgNO3 solution to reach the endpoint? And we're given the relevant chemical reaction, AgNO3 aqueous plus NaCl aqueous goes to form solid AgCl and aqueous NaNO3. So I'll be the first to admit that a problem like this can be very intimidating. There's a lot going on, there are a lot of details, and it's very easy to lose track of what's going on. So I want to step you through this and think carefully about how we can attack a problem like this. So first things first, what's the question asking us? Well, we want to know the concentration of sodium chloride in a solution. So we've got a solution of sodium chloride and we want to know its concentration. Okay. We're also told that we have 15 milliliters of the solution. So the volume of this sodium chloride solution that we're testing is 15.00 milliliters. Okay, so far so good. Now I'm going to switch to a different highlighter and continue, and we're titrating the sodium chloride with a 0.2503 molar solution of silver nitrate. So this is the substance B that we're adding to determine the amount of the sodium chloride that we've got. And so we're introducing this second solution. And so the second solution is going to be added, and that solution is silver nitrate. it has a concentration of 0.2503 molar. And then the question also tells us that the amount of that silver nitrate solution was 20.22 milliliters. That was the volume that it took in order to reach the end point of the reaction. Okay, so we've got sodium chloride that we're trying to measure. We're adding silver nitrate, and these two substances are related by the chemical equation that's given. So sodium chloride reacts with silver nitrate, and we can see that they react in a 1-to-1 ratio. Okay, so here's how we're going to approach actually solving this problem. So we know that in order to reach the endpoint, we had a volume of silver nitrate of 20.22 milliliters, and we also know the concentration of the silver nitrate. So given the volume and the concentration, we can figure out how many moles of silver nitrate were added. So that, again, that's our substance B. We'll figure out how much of that we added, and then at the end point, the amount of substance B is in a stoichiometric ratio with the amount of substance A. And so in this case, the reaction stoichiometry is 1-to-1. 1 mole of sodium chloride reacts with 1 mole of silver nitrate. So this relationship will let us find the number of moles of sodium chloride. And then finally, we know the volume of our sodium chloride solution was 15 milliliters. And so we'll use that to work out the concentration of the sodium chloride. Okay, so I'm going to start off with the part of the calculation concerned with the silver nitrate. And so I'll continue using the green highlighter for this. We've got 20.22 milliliters of silver nitrate. And then I'm going to want to work out the number of moles. And since I've got a molar concentration, that's moles per liter, I first need to convert this into liters. So I use the fact that there's 1,000 milliliters in a liter. So then the milliliters will cancel. And then I can multiply by the conversion factor to go from liters to moles, and that's given by the concentration. 1 liter of the silver nitrate solution contains 0.2503 moles. Then the liters cancel out. This will give us the number of moles of silver nitrate, and then the reaction stoichiometry lets us convert from moles of silver nitrate to moles of sodium chloride. These are in a 1-to-1 ratio, and so the moles of silver nitrate will cancel. And when we multiply and divide all of this, we find that the number of moles of sodium chloride that reacted was 0.005006 moles. And so now, in order to convert this into a concentration, we'll just take this number of moles and divide by the volume. One thing you want to be careful of, we're trying to find the concentration of the sodium chloride in that original solution that we were testing. And so when we divide by the volume, we're dividing by the original volume of that sodium chloride, which was 15 milliliters, or 0.01500 liters. So we'll take the number of moles of sodium chloride that we just worked out, we'll divide by the volume in liters, and that gives us 0.333733 moles per liter of sodium chloride, and then we'll round off. And in this case, all of the numbers that went into our calculation were either exact or had precision of 4 significant figures. So we'll round this off to 4 significant figures, and we get that the concentration of sodium chloride is 0.3337. Okay, so titrations are a very widely used technique. There are other techniques out there that are faster and easier for measuring amounts of substance, but One of the nice things about titrations is that they are very, very precise. You can see from this example that we're able to get out 4 significant figures of precision from a titration. And so anytime you're doing, anytime you want to determine the amount of a substance with high precision, titration is a great technique to use. And so this is often used in environmental testing, for example, to measure the concentration of pollutants in, say, a river. It's also used in medical testing. Anytime a doctor takes a blood sample for testing, very often that the tests will be done using titrations. So titrations are a great way of doing high precision measurements of the amount of a substance, and that wraps things up for today.